Okay, so first of all, let's start to review our the things that we talked about before. Okay, so let's do one more net ion equation questions. Okay, so this one. This one, we have sodium chloride, which is a sodium chloride. This is a page 16, I think, page 16. Okay, sodium chloride react with strontium sulfate. Strontium is a +2 charge, so strontium sulfate. And then they're going to have a double displacement reaction, which means sodium is going to combine with sulfate and chloride will combine with strontium. Okay, so now since strontium has 2 positive charge, then you need to combine with the chlorine with the 2. Okay, not just the 1 chloride. You need to have a 2 chloride to make a neutral, and then your plus the other one is a sodium sulfate. Okay, sodium sulfate. Okay. Sodium sulfate, that's definitely is aqueous. So the only precipitate probably is just a strontium sulfate, chloride. Okay, so that's strontium chloride. Yeah, so that's gonna be a solid over here. Then again, you can split those ions. Before we do so, we need to, balance the equation. 2 sodium chloride. Okay, put one up here, and one up here. Then that should be balanced. Okay, so that's the molecular equation. For the net complete ion equation, well, we're gonna know sodium chloride is dissolving the solution. So we put AQ, strontium sulfate is aqueous, and then this is aqueous. This one is a solid. So what are you gonna write? You're going to write this as sodium ions, 2 of the sodium ion plus 2 of the chloride ion, and the plus strontium ion and plus sulfate ions. Okay, once again, you have to write the charge. Okay, if you're not write charge, I'm going to assume this is a metal. Okay, if only you write charge, then I think this is ion. Okay, if without charge, that's a metal. Okay, sulfate to form strontium chloride and the plus sodium, 2 of the sodium ion and 1 of the sulfate ion. Aqueous. Strong chloride, since there's a solid, there's non-electrolyzed, so you cannot split that in the ion. So now you will see, okay, sodium here, 2 sodium and 2 sodium ions over here, 2 chloride ion, and 1 sulfate ion, 1 sulfate ion. So those are spectator ions. The left over, like a 2 chloride ion plus 1 strontium, and to form strontium chloride solids. Okay, and the spectator ion will be just the sodium ion and sulfate ions. Okay, so now that's gonna be just the structure, the net ion equation. So in general, if you see this again, you will realize net ion equation, that's just a precipitate plus the ions that made this precipitate. That's it. Okay, yeah. So today we're going to repeating these things in the lab for the net ion equation. Okay, so this is one of the example for this one. And also last time we talked about the oxidation number. Hopefully you still remember the oxidation number. So we talk about if we have like a potassium cyanide, cyanate, okay, potassium cyanate. And if you want to figure out the oxidation number for each of this, well, then the potassium, the ions is the oxidation number is the charge, right? So potassium, this guy is a potassium ion up there. So this guy has a 1 positive charge. So you just, the potassium has a 1 positive charge. And we talk about oxygen for any of the compounds, doesn't matter it's ionic compound or metallic compound, they always -2. So there's a guy -2. And the only thing you don't know is this one. So you just figure out, okay? So since the sum of the oxidation number is equal to 0, okay, for the compound. So 1 times 2, you plus selenium, and you plus the -2 times 4, that should be equal to 0, okay? So now is 2 plus selenium plus minus 8, that should be equal to 0. So selenium is +6. Again, if the oxidation number is a positive, so please write a plus in front, okay? So if it's positive, please write a plus, okay? Again, if we are talking about the oxidation number for the polyatomic ion, again, so phosphor is, we're trying to figure out oxidation number for the phosphor. And we know oxygen is -2. So phosphorus plus -2 times 4, that's oxidation number. That should be the sum of the oxidation number in a polyatomic ion should be equal to its charge. This charge is 3 minus, okay? So now is a P minus 8 equal to -5. So P will be equal to +5, okay? P will be +5. So that's the oxidation number for the phosphate, for the phosphorus in the phosphate, okay? Yeah, so this is what we talk about for the oxidation number. And last time we talked about, okay, how to work on the stoichiometry for the mole-to-mole ratio stoichiometry. This is, okay, if we know mole of one compound and we try to figure out mole of another compound, and this is what we call the mole-to-mole ratio stoichiometry. Mole-to-mole ratio stoichiometry. So you just need to, based on the coefficient, to figure out the mole of the other. Let's just work on this. Okay, first of all, you need to balance these equations. Okay, I'm going to add 2 over here since we have 1 chlorine. So we have a 2 over here, and then we'll have 2 of this and 1 of this. So now this reaction is balanced. And again, this is a single displacement reaction, right? Single elements plus a compound to make another elements plus new compound, okay? So now here the question talk about how many moles of chlorine are needed to produce that much mole of iodine. So now we have a 0.4789 mole of the iodine. We try to figure out the chlorine. Well, if you look at this question, you don't even have to do the calculation because you see this is 1 and this is 1:1 ratio, which means the same, they should have a same moles, right? Because the coefficient, if the coefficient is the same, the mole should be the same, okay? Because the relationship is 1 mole of the chlorine gases should form 1 mole of the iodine, okay? Now we have a 0.4789 mole of the iodine, and then we're going to time a fraction to cancel the mole of iodine to get mole of the chlorine gases. Well, then that's going to be just a 1:1 ratio, right? Since this shows 1:1. So now the answer should be the same, 0.4789 mole of the chlorine gases, because the iodine is being canceled. The leftover unit is just a mole of the chlorine. Okay, so the answer will be like this. Then next one, how many mole of a barium cyanide are needed to produce 12.0 moles of barium sulfate? Okay, so now we're asking for the mole of the barium cyanide. And what we have a 12.0 mole of the barium sulfate. Okay, we have this. So first of all, we need to balance this reaction. So we put this as a 1, and this is going to be 1, and we have a 2 of this, and then we're going to put a 1 of that. Okay, so now we have a 12 point, again, you see, this is still 1-to-1 ratio, right? So if it's 1-to-1 ratio, then you even don't have to do the calculation. The result that should be 12.0 mole, okay, because that's a 1-to-1 ratio. And if you don't believe it, okay, let's put that into the equation. We have 12 mole of the barium sulfate, and then you're going to cancel the mole of barium sulfate, and then you can got the mole of the barium cyanide. Okay, so now 1 mole of the barium sulfate need 1 mole of the barium cyanide. Okay, so now you say mole of the barium sulfate canceled, you got 12.0 mole of the barium cyanide. Okay, yeah, so that is just a fundamental for the stoichiometry. That's the backbone of the stoichiometry. If you got a mole of something, you can, based on the coefficient, you got a mole of the other. Okay, yeah, so this is what we call mole to mole ratio stoichiometry. And today we're going to talk about another stoichiometry, and that is called a mass to mole and the mole to mass stoichiometry. Okay, so let's talk about some of the information. Okay, so first of all, let's solve this problem. Okay, this one is talk about the amount of the chloride ion in a water sample is to be determined by adding excess silver nitrate. 1 gram of the silver chloride is a precipitate, and asking for what is the mass of the chloride ion is in the original samples. They're asking for what is the mass of the chloride ions in the original sample. Well, here, this is, okay, again, originally they're giving some of the mass, right? They're giving the mass, which is give you the unit is in gram, right? They know some of the mass. So, and remember, when we do the stoichiometry, we're talking about the mole ratio, right? We're not talking about the mass ratio. So that is why the first thing is you need to convert this mass to mole of something, okay? To mole of something. Because we're talking about the mole ratio. We're not talking about mass ratio. You cannot directly using the mass. Instead, you're going to using mole. So that's why you're gonna convert the mass to the mole. And then you based on the mole, just like what we did previously, okay, using the mole to find the mole of another stuff. And then the question asking for, again, another mass. So you're gonna convert the mole of this to the mass again. Okay, so that's why we call this stoichiometry. It's called the mass to mole, mole to mass stoichiometry. Okay, mass to mole, mole to mass stoichiometry. Okay, so let's work on these questions. So let me put this on the side. What we have chloride ion. So they said they have a chloride ion. They're going to put unlimited or excess silver nitrate over there. They're going to put excess silver nitrate. Silver nitrate, that's a soluble because nitrate plus any of the cation, that's a soluble. Okay, yeah. So the chloride ion definitely is also soluble. And then they're going to making silver chloride precipitate, which means this guy is a solid. This is non-electrolyte. Okay, and then they're going to have, by the way, if I write this, the other one, what is the other one? Chloride react with silver nitrate. What is that? That's going to be nitrate ions. Okay, that's going to be nitrate ions. Okay, so now this is the setup. Okay, this is chemical reaction. Let's see. First of all, when you do stoichiometry, I strongly recommend you write equation and write what you have underneath this equations. For example, what we have 1.0 gram for the silver chloride. Okay, and then what we're asking for? We're asking for what is the mass? What is the mass of the chloride ion? Okay, so now what is the step we're gonna do? The pathway again. So you have the mass of this, and then we are not using mass, we're using mole. So you're gonna convert that to the mole of the silver chloride first, right? And then you based on the mole of the silver chloride and to figure out mole of the chloride ion, and then based on the mole of chloride ion to got mass of the chloride. So that's we got 3 steps. Okay, so compared to the previous stoichiometry mole to mole, that's just 1 step, but right now we have 3 steps. The fundamental part is we need to convert the mass to the mole. Okay, or we count the mole to mass, because when we do stoichiometry, we can only using mole to do the stoichiometry, not in the mass. So that's why we have additional steps. You convert the mass to the mole or convert the mole to the mass to fit the question. Okay, yeah, so that is the fundamental thing. Well, before we're doing anything, we need to balance this equation. Yeah, looks like it's already balanced. Okay, then you will see that's all just 1, 1, 1, 1. So everything is 1-to-1 ratio, right? So now, first of all, we need to figure out the mole of this. Okay, yeah. Again, you can do 2 different ways. Okay, you can do this reaction step by step, or just making a long equation to calculate and to put all the steps together. Okay, it's up to you. Okay, well, just to let you know, the long step is more faster to do the calculation. Okay, yeah, but if you're not familiar with that, then you can do that step by step. Okay, so we will do 2 different ways to solve the problem. So let's just do step by step. Okay, so first let's do step by step. I'm going to just do step by step for this question, but for the rest of the others question, I'm going to just making a long equations. Okay, so here the step by step is just showing you how to do this. Okay, so remember we have a 1, 2, 3. We have 3 steps. So you're gonna do the 3 steps over here. The first step, you convert mass of the silver chloride to the mole of the silver chloride. So the mole of the silver chloride, again, remember mole is equal to mass over molar mass. Okay, that's going to be equal to mass of the silver chloride divided by the molar mass of the silver chloride. Okay, so the molar mass of silver chloride is already gave you, and 143.25. Okay, so now you have a 1.0 gram and divided by 143.25 gram per mole. Okay, and then you got a number. So I'm going to write down this number. 1 divided by 143.25. So you got a 0.00698. Okay, 0.00698. Again, don't round this number to 0.007. Okay, you only have one sig fig. That's not enough. We need a more sig fig for the question. Okay, yeah, we need a more sig fig. So this is the how many mole for the silver chloride. Okay, then the second step is the stoichiometry. Okay, second step talk about if we have that much more, how many more of the chloride ion do we have? Well, if you look at this, the coefficient, that's a 1-to-1 ratio, right? 1 mole of the silver chloride need 1 mole of the chloride ion. So that's 1-to-1. Now you're going to figure out the mole of the chloride ion. Then that's just equal to 0.00698 mole of the silver chloride. And then you're going to time a fraction. That's a 1 mole of the silver chloride need 1 mole of the chloride ion. So now silver chloride canceled. Now you still got 0.00698 mole of the chloride ion. So now we figure out moles of the chloride ion. Then what are we going to do? The question asking for how many mass of the chloride ion. Then you have to convert the mole, you convert the mole of the chloride ion to the mass of the chloride ion. The mass of the chloride ion, again, mass equal to mole time molar mass. Mole time molar mass. So 0.00698 mole of the chloride ion. Then you're going to time molar mass of chloride. Molar mass of chloride is 35.453. 35.453. That's in gram per mole. And you will see mole and mole are canceled. So now you will get the gram of the chloride ion. And just go ahead, put that into the calculator. 0.00698 times 35.453. And you got a 0.2475. 0.2475 mole. Okay. Sorry, in gram. This is in gram. So that's a mass of the chloride ion. Okay. Now let's see what is a sig fig we need to keep for this question. This question actually don't give you too many. They are only give you one number. Again, molar mass, we will assume the molar mass will be as a conversion factor. So we're not going to using molar mass to count the sig fig. Okay, so the question only just give you 1.0 gram. So we will just keep 2 sig fig for this question. Okay, so that is why the answer will be 0.25. Okay, will be just a 0.25 gram. Okay, 0.25 gram. Are you clear? So this is called a mass to mole, mole to mass stoichiometry. The backbone is still mole to mole. But the point is you need to convert the mass to mole to figure out the stoichiometry. Okay, that is the key. Okay, so now let's see the second question. The second question, let's see again. This is talk about how many moles of the manganese, are in 286 grams of the magnesium oxide. Okay, so let's see. This is a manganese 3 oxide. So we have manganese 3 oxide. Okay, that's a solid. Well, this one, they're asking for how many magnesium ion in there. Well, so then what we do, you can just, you can also write equations, okay? How many manganese in this compound? Well, you have 2 manganese ions over there, right? How many oxygen ions in there? Well, we have 3 oxygen ions over there, right? So generally, you still can set up the similar equations. The question asking for, okay, I know the mass of the magnesium oxide. Again, what is the mass again? 286 gram, okay? And then we're going to figure out what is the mole of this? What is the mole of the manganese, right? Okay, still, you're going to have the coefficient, you still can based on the stoichiometry to figure out that, okay? So what do you do? Again, the coefficient over here still is in mole, right? So you have to figure out the mole of the manganese oxide, and then you can directly figure out the mole of the magnesium ion. Okay, now you don't have to calculate the mass of the magnesium ion because the question asking for how many mole. Okay, yeah, so now you have only 2 steps instead of 3 steps. Okay, yeah, so now we can using the long equation to do this work. Okay, we're using the long equation. So now you have what we have a 286 gram of the magnesium oxide. So this is a magnesium 3 oxide. And then we're going to convert the mass to the mole, right? So we're going to put the mass of the magnesium oxide over here. And again, you're going to divide by the molar mass. And then you will get the mole of the magnesium oxide. Okay, so what is the molar mass of the manganese oxide? The question should already give you 157.88. 157.88 divided by 1.157.88. Then you can get 1 mole of the magnesium oxide. Okay, so you see gram and the gram are canceled. Now you got mole of the magnesium oxide. And then we time another conversion factor because we're done this part. This is the first step. Second step, you're going to convert the moles of the magnesium oxide to the manganese. Then you will see, well, here, this is a 1:2 ratio. So you need to cancel the moles of the manganese oxide to get mole of the manganese ion. Manganese ion. Well, you may be, I know here somebody will confused. Should I got 2 magnesium ions? Okay, should I write 2 magnesium ions? No, you are not going to. Okay, the 2 is a coefficient. You're gonna put the coefficient over there as in a calculation. So now you see in front of magnesium oxide is 1, so you put a 1 over here. In front of magnesium ion is 2, so you put a 2 over here. Now, you see more of the magnesium oxide, more of this are canceled. Now the last unit is just more of the magnesium ion. That's it, okay? So what do you do for the calculation? You just have a 286 times 1 times 2, that's top part, divided by 157.88 times 1. And the unit will be just mole of the magnesium ions. Okay, then you put that into your calculator. 286 times 1 times 2 divided by parenthesis 157.88 times 1 parenthesis. And the answer will be 3.623. Okay, 3.623. And this unit, that's going to be mole of the magnesium ions. Okay, mole of the magnesium ions. But we need to double check the sig fig. The question has a 3 sig fig, so answer will be 3 sig fig. So the answer should be 3.62 mole of the magnesium ions. Okay, manganese ion. So let's see. 3.62 mole of the magnesium ion. Are you clear? Okay, yeah. So this is what we talk about the mass to mole, mole to mass stoichiometry. Okay, mass to mole, mole to mass stoichiometry. All right, so please go ahead, work on the question number 3 over here. So let's just test whether you got it or not. Okay. Raise your hand if you're done. Okay. So let's review this question. Okay. Okay, so now this question, the asking for what mass of the ammonium perchlorate. So we're asking for mass of that. And then what we have a 20 gram of the aluminum. So we have a 20.0 gram of aluminum. Okay, so here, this is a very, very common mistake people make. Okay, so they said, okay, 20 gram of this, we have a 10 to 6. So now we will have a 12 gram of the ammonium perchlorate. This is not right, okay? Because you're using 20 gram. Sorry, not, oh yeah, 20 gram over here is gram, that's a mass. You cannot using the mass value to make a ratio because this 6 and 10, 6 versus 10 is a mole ratio. It's not the mass, okay? So you cannot using the mass to make a ratio to get this 12 gram, okay? You have to using mole ratio. So that's why you have to convert the mass to the mole, okay? Because the 6 verse 10 is talking about 6 mole of this compound, you're gonna react with 10 mole of that. It's not a 6 gram of this to react with 10 gram of that, okay? So you have to convert that to the mole first, okay? You have to convert the mole first. So that's why, again, 3 steps. First of all, we have a 20.0 gram of the aluminum. Then you're going to convert the mass of aluminum to the mole of aluminum. You're divided by the molar mass, right? Gram divided by molar mass, you got a mole. So you have a mass of the aluminum to got the 1 mole of the aluminum. Okay, the molar mass is just 1 mole of the aluminum to got how many gram? That's a 26.98. 26.98. It already shows over here. Okay, and then you cancel the gram, you got a mole. And then based on the stoichiometry, you see, you need to convert the mole of the aluminum to the mole of the ammonium chloride. No, perchlorate, ammonium perchlorate. So based on the stoichiometry, 10 moles of aluminum, you will generate 6 mole of the ammonium perchlorate. So this also unit canceled. Now you got mole of ammonium perchlorate. And then you have one more step. In this case, you're gonna convert the mole of the ammonium chlorate again. Again, once you have a mole, you multiply the molar mass, then you got a gram. So mole of the ammonium perchlorate to got the gram of the ammonium perchlorate. Okay, so 1 mole of ammonium perchlorate is equal to 117.49 gram of this. Okay, so now you see mole of this are canceled. Now what are you gonna do for this calculation? Just time everything on the top, you're gonna time together 20.0 times 1 times 6 times 117.49. And in the bottom part, you have a parenthesis 26.98 times 10. Okay, make sure you have a parenthesis for the bottom parts. Okay, when you type that in your calculation. Now you have a 20.0 times 1 times 6 times 117.49 divided by parenthesis 26.98 times 10. And then you got a 52.256. 52.456 gram. Okay, that's a gram. And then you see answer The question only gave you one number, 20.0. Okay, so 3 sig fig. So the answer will be 52.5 gram. Okay, 52.5 gram. I don't think that. Did you got the 52.5 or 52.3? Let's see. Oh, okay, 256. Okay. Yeah, so that's one is a 256. 256. So now this should be 3. Okay. Yeah, 52.3 gram. You see, this is generally what we talk about the stoichiometry. Not that hard, right? Not very hard. Okay. Yeah. So we need to continue to do the practice. Okay. Continue to do the practice. So the next part, let's take a break and then we will talk about the next topic. Okay. It's still in stoichiometry, but another different topic. Okay. Okay, so the next part, we're going to talk about limiting reagent. Okay, I prefer to put the video on this, then you can easily to understand what does that mean for the limiting reagent. Well, again, limiting reagent is still part of the concept for stoichiometry. It just have a different way to solve the problem. Okay, yeah, so let's look at this.
Way, we'll also discuss a related topic called excess reactant. Now, limiting reactant, excess reactant, this stuff all has to do with chemical reactions. But to explain it from the beginning, I actually don't want to start talking about the chemistry.
Instead, I want to start talking about some analogies to cooking. We'll compare a chemical reaction to a cooking recipe. Let's say you're having some friends over for a barbecue, and you want to make some cheeseburgers, all right? Here's what you're going to need to make them. You're going to need a bun, you're going to need a slice of cheese, and you're going to need a piece of meat. Now, since we're comparing chemistry and cooking, we can write the recipe for this kind of like a chemical equation, all right? Here it is. 1 bun plus 1 slice of cheese plus 1 piece of meat, put that all together, and it gives us 1 cheeseburger. The ingredients over here that we start with, we can think of those kind of like reactants in a chemical reaction, and the products over here, cheeseburger, is what we end up with. Okay, so now we've got our recipe. To do some cooking, we got to get some more ingredients. Let's rummage around in the refrigerator, see what we can find. So here are our ingredients. And you'll notice we have different numbers of each one. This happens a lot in cooking, and it also happens a lot in chemical reactions. You often start with different amounts of each reactant. So we're talking about limiting reactant here. And limiting reactant comes into play when we ask the question, given these different numbers of ingredients, what is the greatest number of cheeseburgers that we can make? All right? We've got 4 buns here. We got 9 slices of cheese. But if we've only got 3 pieces of meat, we can really only make 3 cheeseburgers, right? Check this out. Here's a first cheeseburger. Here's a second one. And here's the third one. And then we run out of meat and we can't make any more cheeseburgers. If this were a chemical reaction, we'd say that meat is the limiting reactant, okay? Here's a definition for you. Limiting reactant is the first reactant that's used up in a reaction. When the limiting reactant is all used up, no more product can form and the reaction stops. So clearly, meat was the first of these ingredients that was used up as we were making the cheeseburgers, and as soon as we use it all up, no more product can form. We can't make any more cheeseburgers and the whole process has to stop, right? We call it limiting reactant because it limits how much of the product we can make, right? It doesn't matter if we have 1,000 buns or 100 slices of cheese. Once we run out of those 3 pieces of meat, we're done. We can't make any more cheeseburgers. So the total number of cheeseburgers that we can make is completely dependent on the amount of the meat, the limiting reactant that we have. So after we run out of the meat, we still have some extra ingredients left up here. And these are what we call excess reactants. Excess reactant is what is left over after the reaction stops because the limiting reactant got all used up, okay? So we have some excess reactant. We got the bun here. We have 1 excess bun, and then some more excess reactant. We have 6 pieces of cheese that are left over after the meat gets all used up. Okay, so now that we've talked about the concepts behind limiting reactant and excess reactant, let's use this information to solve some problems that are a little bit more advanced. This looks more like a chemical equation, but we're still cooking here. I'm pretending that this is a recipe for bread rolls. It would actually be a terrible recipe. It's just flour and water. I definitely wouldn't want to eat these bread rolls, but this is going to be great practice for limiting reactant and excess reactant. So we're going to use this recipe or this equation to solve the following problem. What is the greatest amount of bread rolls that can be made with 6 cups of flour and 3 cups of water? If this were a chemical reaction, what would be the limiting reactant? Which reactant is in excess and how much is left over? So we want to make the greatest amount of bread rolls with 6 cups of flour and 3 cups of water. Let's get these ingredients out here. Here they are. Now to figure out the greatest amount of bread rolls we can make, we first have to identify which of these ingredients is a limiting reactant. Now that's a little bit trickier than it was with the cheeseburger problem we just did. We can't only look at these and figure out which is a limiting reactant. Instead, we're going to have to solve this problem like this. We're going to start with, say, the flour, and we're going to ask if we want to use the maximum amount of this flour, if we want to use all 6 cups, how much water are we going to need? Do we have enough or is it going to run out? And then we're going to switch and we're going to do the opposite. we're going to ask if we want to use the maximum amount of water, we want to use all 3 cups of this, how much flour do we need, and do we have enough, or is it going to run out? Okay, let me show you what I mean. Let's start with the flour. Okay, we got 6 cups here. Now this recipe is only for 3 cups. So what if you were in the kitchen and you actually wanted to make this recipe with 6 cups of flour instead of 3? What would you do? Well, you'd double it. You'd multiply everything by 2. Okay, so we can multiply this by 2 to make the recipe with 6 cups of flour. Now, if we're using 6 cups of flour, how much water do we need? Well, we can multiply this by 2, which will tell us that we need 2 cups of water to go with the 6 cups of flour. And finally, how many bread rolls is that going to make? Well, we're just doubling the recipe. So instead of 5, we're going to end up with 10. Okay, so that's for trying to use the maximum, the 6 cups of flour. What are we going to need in terms of flour if we want to use the maximum amount of water? Okay, we got 3 cups of water. Okay, the recipe is for 1 cup of water. So it's kind of like we got to triple the recipe. We're multiplying 1 by 3. How about the flour? How much flour are we going to need for 3 cups of water? Well, we triple this. So we have 3 times 3. We're going to need 9 cups of flour. How many bread rolls are we going to get? Triple the recipe. 5 times 3, 15 bread rolls. All right, so here's all of our information. What's the greatest amount of bread rolls that we can make? Well, one of these situations isn't going to work because we're going to run out of one of the ingredients. Okay, let's take a look at this. If we start with 6 cups of flour, we need 2 cups of water. Do we have that? Yeah, we do. We have 3 cups. We actually have more than enough. So this would work. We could make 10 bread rolls. What if we start with 3 cups of water? Then we need 9 cups of flour. But that's not going to work because we only have 6 cups of flour. So we can't make 15 bread rolls because we don't have enough flour. The flour is going to be the first ingredient or the first reactant to run out. So that means that flour is the limiting reactant. It's going to limit the amount of bread rolls that we can make. So flour here is the limiting reactant. Now we can also show this visually, okay? Imagine that we're kind of cooking this recipe, okay? 3 cups of flour and 1 cup of water get combined, okay? So here are 3 cups of flour, 1 cup of water. We take them, put them in the oven or whatever, and we get 5 bread rolls. 1, 2, 3, 4, 5. Okay, let's do that again. Another 3 cups of flour, 1 cup of water, combine them, and we get 5 more bread rolls. 1, 2, 3, 4, 5. And now you can see the flour has run out. The flour is the first thing to run out, so it's the limiting reactant. We still have 1 cup of water here, and that's excess. That's what we'd call our excess reactant, 1 cup of water that's left over after we run out of the limiting reactant. Okay? So that's how you solve these kind of problems. You say, I want to use a maximum amount of flour. How much water do I need and do I run out? And then you say, I want to try using the maximum amount of water. How much flour do I need and do I run out of that? Now here's a really important thing to mention. There's a common misconception that limiting reactant is the thing that you have the least of. But that's not true, right? Look at the example that we just did. We had more flour than water, but flour was the limiting reactant. And that's because limiting reactant isn't the thing you have the least amount of. It's the thing that runs out first. So even though we had more flour than water, when we're following this recipe, the flour gets used up before the water does. So that's why the flour is a limiting reactant, even though we have more of it. So keep that in mind. Anyway, now that we've worked through this problem, let's finally look at an example that uses a real chemical equation. Here's a chemical equation, and we're going to use it to answer this question. What is...
Okay, so that's the video we're talking about. We're introducing 2 concepts. One is called the limiting reagent. The other one is the excess reagent. Okay, yeah. So how much of the product that can be produced is really depends on the limiting reagent. It's not depends on the excess reagent, right? Limiting reagent, again, the concept for limiting reagent is the one that used up first, okay? It's not the smallest amount, okay? In another word, if I give you the mass or the moles of each of these compounds, you cannot based on the mole or mass to determine which one is a limiting reagent. You have to follow the calculation to figure out which one is a limiting reagent. Okay, yeah. So now I'm going to do one of the practice, and this practice again is different from the one that from those topic. Yeah, and I'm going to talk about the other one, and another way to figure out the limiting reagent. I think my way is more easier than the topic. Yeah. Okay, so let's look at the last page, question number 10. And this question is more like, well, wait, let's. Okay, let's look at this one. Okay, question number 7. This one is more easy. Okay, question number 7. So this question 7, again, this is still a part of the stoichiometry question because we need to using stoichiometry to figure out which one is a limiting reagent. Okay, yeah, so let's see this question. And we have a mixture of a 4.5 moles of the aluminum. And we have a 3.5 mole of the oxygen is allowed to react, and identify the limiting reagent and or limiting reactant. Limiting reagent is also called the limiting reactant. Those are the same thing. And determine the amount of excess reactant, amount of the excess reactant. Okay, so let's talk about this. Okay, so my way to determine which one is a limiting reagent, which one is the excess reactant. What I do is you're based on, okay, so first, again, we still need to do, okay, what if we're using up 4.5, if we use up all of those 4.5 moles of aluminum, then we calculate how many moles of the aluminum oxide is going to use, okay? Second one, if we use up all of the 3.5 moles of oxygen, then how many moles of the product that is going to generated, okay? And then we're going to compare those two numbers, okay? We're going to compare the moles of the moles of the product that based on the aluminum and based on the oxygen, and to figure out which one is the smallest amount. Okay, yeah, so let's work on this. So first one, let's see if we use up all the aluminum. So, we have a 4.5 mole of the aluminum. If we use up all the aluminum, how much moles of the aluminum oxide that we can produce? Okay, we're going to convert that to the aluminum to moles of the aluminum oxide. Okay, so if you look at the coefficient, 4 moles of aluminum will produce 2 moles of aluminum oxide. Okay, so now you can do the calculation. 4.5 times 2 divided by 4, you got 2.25. Okay, 2.25 mole of the aluminum oxide. Okay, so remember, this is the result that based on if we use up all of the aluminum, that how many moles of the aluminum oxide that we can produce. The second part, okay, you're going to make a assumption that if we use up all the oxygen, that how many moles of the aluminum that we're going to produce. Okay, so now we based on the moles of oxygen, we have 3 moles of the oxygen. And then if we use up all the moles of oxygen, how many moles of the aluminum oxide that we can produce? Well, if you look at the coefficient, 3 moles of the oxygen will generate 2 moles of the aluminum oxide. And then you can figure out, okay, so looks like there's gonna be 2 moles of the aluminum oxide that we can produce. Okay, 3 times 2 divided by 3, that's 2 moles. Okay, so now you can see 2 moles of the aluminum oxide we can produce. Now here we got 2 different number for the moles of the aluminum oxide. That depends on the 2 different reactants. 4.5 moles of aluminum will produce 2.25 moles of the aluminum oxide. 3.5 moles of oxygen will generate 2 moles of the aluminum oxide. And then you just need to compare those 2 numbers. And I give you the conclusion. The smallest mole number, okay, the one that produce the smallest mole will be the limiting reagent. Yes, Cora. Oh, okay. Yeah, good point. Yeah. 3.5, that should be 3.5. Okay, because this guy is 3.5. Okay, yeah, we have a 3.5 moles. Then let's see which one is. Okay, 3.5 times 2 divided by 3. And you got 2.333. Okay, so then it's completely different. Okay, so this guy, you have a 2.33. Okay, 2.33 mole of the aluminum oxide. Well, then that's gonna be, this gonna change the story. Okay, this gonna change the story. Okay, yeah, 4.5 moles of aluminum produce 2.25 moles of the aluminum oxide. 3.5 moles of the oxygen produce 2.33 moles of the oxygen. Which one is bigger? This one is bigger. Which one is smaller? This is smaller. So the one that produces the least amount of the product is the limiting reagent. Okay, which one produces the least amount of product? Aluminum. Aluminum produces the least amount of product, so aluminum will be called the limiting reagent. Okay, yeah, aluminum will be called the limiting reagent. Okay, aluminum will call the limiting reagent. The other one, oxygen, will be called the excess. Will be called the excess agent, reagent. Okay, so aluminum, the one that produces the least amount of the product will be called the limiting reagent. So aluminum here, they produce 2.25 moles of the aluminum oxide. So aluminum will be called limiting reagent. The other one will be called the excess reagent. Okay, yeah. So then the aluminum will be the limiting reagent and the oxygen gases will be the excess reactant, okay? But the question asking for what is the amount of the excess reactant, which means if you use up all the aluminum, how much moles of the oxygen will left over, right? This is talk about determining the amount of the excess reactant. It's talk about if you use up all the aluminum, the reaction is stopped, okay? So reaction stopped, okay? How many oxygen is left over here, okay? Then you need to calculate, okay? So now you need to calculate, okay, if we use up 4.5 moles of aluminum, how many of the oxygen do we need to use up? Okay, how many oxygen do we need to use? So you need to calculate how many oxygen you need to use when you use up all the 4.5 moles of aluminum. Okay, so now you have a 4.5 mole of the aluminum. Then we need to figure out how many moles of the oxygen that is going to be used up. Okay, so now based on the coefficient, 4 moles of aluminum need 3 moles of oxygen, and then moles of aluminum is cancelled. Now you can figure out 4.5 times 3 divided by 4. You got 3.345. 3.375. 3.375 mole of the oxygen. So we use up that much of the oxygen. Then how much oxygen is left over? Well, then what are you going to do? Originally, we have a 3.5. We have a 3.5 mole of the oxygen. And then you subtract the moles of oxygen that you already used. 3.375 mole of the oxygen. This is the one that already been used, and the difference will be the leftover, right? The difference will be the leftover. The leftover 3.5 minus 3.375, you got 0.125. Okay, so you got a 0.125 mole of the oxygen. Okay, so that is how much of the oxygen that left over. Okay, so this is the amount of the excess reactant. Okay, yeah, hopefully you understand the concept. Okay, we are trying to figure out first in this kind of question, you first need to figure out what is the limiting reagent, and then the limiting rate, then which one is the excess. Okay, and then we can figure out the other questions. Corey, do you have a question? You good? Okay, yeah. So this one is easier because we're still using mole this, mole that. Okay, but what if we're talking about some of the mass instead of mole? So let's look at one of the questions. Well, so this one is a conceptual question, but they're not using a certain compound, but using just X, Y, Z. But it's still talking about same thing. But here we're talking about something else. Okay, let's look at this. This one for the reaction, we have those 2x plus 3y to form 3z. Okay, the combination of 2 moles of x, 2 moles of y, and they're going to produce 1.75 moles of z in experiment. This is talking about in the lab. Okay, so this is in the lab. And then they're asking for what is the percent yield of these reactions. Well, so I haven't talked about what is the percent yield. So in this case, we have several concepts we're going to introduce. First one is called the percent yield. Second one is called experimental yield. Experimental yield. The last one is called the theoretical yield. Okay, we will talk about those 3 concepts later. But first of all, we need to figure out what is the limiting reagent for this reaction. Is it X or Y? Okay, and also here is the hint. Okay, how can we tell this question is a limiting reagent question or is just a simple stoichiometry question? Limiting reagent question, they will give you the mole or mass for the both reactant. Okay, so this guy is telling you 2 moles of X, 2 moles of Y. So they're telling you the amount for both both two reactants. But for the simple stoichiometry question, they're not going to. They only just telling you one of the reactant. Okay, so for example, in the previous question, those are the stoichiometry question. Those are stoichiometry question. You see, for this question we talk about, they are only just give you one of the reactant, right? They're telling you 20 grams of the aluminum. They are not looking for the rest of others. Okay, so this one only telling you one of this, then they're asking for the other one. So that is called a stoichiometry. Okay, that's called a stoichiometry. The first one is the same thing. They only just give you 1 gram of this silver chloride, and then they are asking for the other things. They don't give you 2 the reactant. They just give you 1 of the reactant. Then that's talk about stoichiometry. Okay. But for the limiting reagent, they will give you both. Okay, that is the difference. All right, so let's look at this again. Okay, so then we know, okay, if we want to figure out the limiting reagent, which one is the limiting reagent? First, you're going to assume if we have a 2.00 mole of the X, how many moles of the Z that we can produce? If we have 2 moles of, if we use up all 2 moles of Y, how many Z will be produced? And then we compare the product. So let's just do this one by one. We have a 2.00 mole of the X, and then we're going to convert how many mole of Z. Okay, so mole of the X need canceled, then got a mole of a Z. So based on the stoichiometry, 2 in front of X, 3 in front of Z. Okay, so mole of X canceled. Now you can figure out that's a 3.00 mole of the Z. Okay, and if we use up all the Y, which is still also 2.00 mole of Y, how many of the moles of the Z that we can produce? Okay, look at the coefficient. 3 moles of Y will produce 3 moles of the Z. So you see that's going to be 2.00 mole of the Z. Okay, so now you see if we use up 2.0 mole of X, we can only produce a 3.00 mole of the Z. Okay, but if we use up all the 2 moles of Y, we can only produce 2 moles of Z. Okay, so you compare those 2 number of product, you will see Y produce less, right? X will produce more. So that is why Y will be called limiting reagent. The one that produces the least amount of product will be called limiting reagent. Okay, will be called limiting reagent. So Y over here, that is a limiting reagent. The X will be the excess. Okay, that will be the excess. Okay, so in this case, we determine which one is a limiting reagent. Okay, then we're going to talk about what is the percent yield, what is the experimental yield, and what is the theoretical yield. Okay, so first, let me just write down what is the equation for the percent yield. The percent yield is equal to the experimental yield divided by theoretical yield and your time 100. Okay, don't forget there's a percent sign. Okay, time 100%. Okay, so that is called the percent yield over here. Okay, so what is the experimental yield? The experimental yield, well, they call it experimental. That means you have to acquire this yield from the experiment. For example, you do some certain experiment, you synthesize some of the crystals, and you generate these crystals. And in your lab, you measure what is the mass of the crystal, okay, or what is the moles of this crystal you get from the lab. And this is called the experimental yield, okay? It's the data that you acquired from this experiment, okay? Yeah, so that is called the experimental yield. Theoretical yield is the yield that is, okay, so based on the stoichiometry, based on the chemical reactions, how much the maximum yield that can be produced from this experiment based on the stoichiometry, okay? Yeah, and just to let you know, the maximum of the yield that you can produce from the experiment is coming from the limiting reagent. In other words, as long as you know which one is the limiting reagent, and based on how much of the limiting reagent that can produce how much of the yield, the product, and the number of the product is called a theoretical yield. Okay, so we just figure out in this equation, we figure out Y is a limiting reagent and how much the product that the Y produced, like a 2.00 mole, then this is what we call the theoretical yield. Any questions? I know this is confusing. Corey? No? Cora? Carol? Question? Okay, so that's why we need to find which one is the limiting reagent, right? As long as we figure out which one is the limiting reagent and the product that is generated is the theoretical yield. That is theoretical yield. So in this equation, if you want to figure out the percent yield, okay, 2.00 mole, they're going to be the theoretical yield because the 2.0 mole of the Z is coming from the limiting reagent Y, okay? Yeah, and what is the experimental yield? And usually the experimental yield should be given in the questions because you have no, I mean, if you do that in the exam, you're not going to able to go to the lab to acquire the experimental yield, right? So generally, the question will give you the number for the experimental yield, but the question may asking you for the theoretical yield or the maximum amount of the yield that can be produced from this experiment theoretically, okay? Yeah. So 1.75 mole of the yield, and then you time 100%, the percentage you get will be called percent yield. 1.75 divided by 2.00, and your time 100, 87.5. Okay, so 87.5% will be the percent yield. Okay, so three concepts. Percent yield. Well, percent yield generally is coming from theoretical yield and experimental yield. Experimental, the top part is experimental yield. Bottom part is a theoretical yield. Okay, again, theoretical yield is the maximum yield that can be produced from theoretically from the chemical reactions. Experimental yield is the yield that you generate from your lab. Then my question is that possible the yield, the percent yield is larger than 100%? Is that possible? Well, in general, it doesn't make sense. Okay, it's not possible because theoretical yield is the maximum yield that you suppose can generate. So your experimental yield more or less is less than that theoretical yield. Okay, but what if some student making the yield percent is more than the percent 100%. Then what that mean? Yes, that means the student did a wrong experiment. Okay, yeah. So they generate a much more experimental yield. So something wrong over here. Either when they weigh the samples, the sample is not dry, so you're containing more water in there. So they gave you more weight for the sample. That makes sense, right? So this is one of the possibility. So anyway, if the percent yield is higher than 100%, that means definitely there's something wrong. Okay, definitely there's something wrong. Does that make sense? Okay, yeah. So generally, this is what we talk about for today. Okay, and we will keep continue for the similar topic in the next class, and we're going to do the worksheet, the study guide on the next class. Okay, yeah.